Hello, I'm James Ingram for AutoControls-dot-org. Welcome to video number 808, which is titled A Demonstration of a DCC-Bitswitch Block Bit Switch. These DCC-Bitswitch units stop DCC trains by suddenly changing the current on the track from DCC to DC current, which causes them to stop. This works on almost all DCC systems that follow the NMRA recommended practice 9.2.4. I'm told it probably won't work on MRC systems because they apparently didn't follow the standards, and it probably won't work on Lionel and MTH systems because they're proprietary systems and apparently don't fully follow the NMRA standards. This video shows a single DCC Bitswitch unit, which is by my hand here, and videos on the DCC-Bitswitch.com website and on the YouTube channels for DCC-Bitswitch and Fred Hughes show more complex operations. Note there's three ways to stop these DCC trains. The way we're using in this video is method number one. We use what DCC-Bitswitch calls a DC break generator, which is this unit right here, which converts DCC to DC, and the bit switch sends it out to the break section when required to stop a train. That's what we're using in this video. The other two ways that we're not using in this video, but just to mention them, is you can also use what DCC-Bitswitch calls a set speed zero generator, which is basically an electronic board, there it is in a protective wrapping, that sends out a set speed zero command, but you need another booster unit to use this unit, so it's a little more complicated and a little more expensive, but this will stop some trains that won't stop using this system. Like I said earlier, if they obey the NMRA recommended practice 9.2.4, this DC signal will work. But on engines that won't obey that, this will usually get them stopped. The third method is what they call asymmetric DCC, which uses diodes to make like an uneven DCC signal. In other words, the positive might be larger than the negative. They cut one side down by using diodes, but this only works for lens and Zemo decoders. These three methods are discussed in more detail by the earlier video, number 803, DCC-Bitswitch Overview, narrated by Fred Hughes. Part 2 at about the 5-minute point starts discussing all three of these methods. The previous video, 807, titled Demonstrating RP 9.2.4, we showed how we set up these engines to stop on DCC, or to stop on DC, to use with this break signal generator. These colored wires on the bit switch here on its center terminals are yellow for test, red for break, green for release, and black for common. Right now the thing is in the green position, so if I hold one end of this wire across the common terminal, I can put it on the break terminal, which will switch it to red. Now if I hold it across the test terminal, which is a yellow wire, there's no light change, but you may hear the relay switch. Now if I hold it on the green terminal, which is a release terminal, it goes back to green. So basically I'm doing here what the reed switches in the track would do when a magnet with a locomotive passes over them. Again, we'll touch the red brake terminal, then we'll touch the yellow test terminal, and we'll touch the green release terminal, which sets it back to green. This drawing is from the DCC-Bitswitch website under the block bit switch part. This is worded probably as well as I can say it, so I'll just read it. It says, when the test contact is triggered, block bit switch simply checks to determine if the leading train has triggered the brake contact, that would be the red light we just threw, but has failed to reach the release contact. If this has occurred, the block bit switch slows the trailing train to a stop using the momentum value stored in CV4, that's the deacceleration variable. Then, reading more, when the leading train has reached the release contact, that would be the green light, and the track contact it sets at the green. When it's reached the release contact, the bit switch will release the trailing train and cause it to accelerate using the momentum value stored in CV3, which is a configuration variable for acceleration. We're back to our drawing from the DCC-Bitswitch website for a simple setup. It refers to this as what's minimum control when you're just using one bit switch. You can have more of them, but this demonstration just uses one bit switch. Here's our DCC command station. Let's go around the loop of track first. Here's the loop of track with the direction of travel clockwise, and the pink part is the brake section. Now over here is the DCC command station, putting DCC current out directly to the main line, and also going to the DC brake generator, which in turn sends both DC and DCC to the bit switch, was shown here in yellow, and then the bit switch connects to the brake section. And then you've got your brake section. And then you've got your three read switches that signal the bit switch. Your green release relay is over here. Your red brake, not relay, read switch, excuse me, your green release read switch is over here. Your red brake read switch is over here, usually not far from the exit of the stopping section, and then inside the stop section shown in yellow here is the test read switch, is the one which actually does the checking to see if it's green or if it's red, and if it's red it switches the current from DCC to DC, which will make the engine come to a gradual stop within the stopping section. Looking at those same components on our little test layout here, here's our North Coast Engineering NCE command station. These two wires here are going out to the track on the main part of the loop. The other two wires coming off the command station, and these are all for DCC. This goes into the brake signal generator. Here's the four wires going to the DCC bit switch. There's A and B terminals, which carry DCC always. Here's C and D terminals, which normally in automatic mode carry DC current. In test mode they'll carry DCC, but normally it's going to be DC going here. Then here's the DCC bit switch stop block unit itself, and it sends the appropriate current out here to the track, either DCC or DC. And this black and white wire goes out over here to the stop section. Then these wires here, the black for common, yellow for the test sensor, red for the brake sensor, and green for the release sensor, go to this terminal block and on out to the track to read switches. Here's the track plan for our little test layout. The main line you could consider starts here, and it goes around through a crossover on the inside, comes back out through this 30-degree crossover and around the outside to the brake section, which is shown in red, and then starting here and going over and ending here is the brake section. And this is electrically isolated. That's what these gaps are supposed to show here. It's electrically isolated on this end and electrically isolated on this end. These have to be gapped and separate, because if you don't, if a train crosses over here or anything causes these to get together, you'll get a short, because if you got DC here and DCC out here, they'll be shorted out at times. So you've got to have this brake section gapped on the end. Now looking at the track contacts, that is to say the reed switches, here's our brake reed switch here in red, and then going as the train progresses around the loop, here's our green release track contact reed switch, and then it's going around the loop and into the brake section in yellow is shown our test track contact. And the logic here is as a train goes through this crossover, it goes over the brake track contact, which sets essentially sets the DCC bit switch to red, which will stop any oncoming train coming through here from getting into the crossover. So you have a train stopped here and a train going around here, and when this train is clear over here, when it's clear of the crossover, then it goes over the green release contact, which will allow this train to start up and enter the crossover without any danger of a collision. And again, going to the logic of this test thing, let's say the thing has been set to red by a train passing over the brake generator. If it's red and a train is entering this section, when it gets to this test section, it will then cause the DCC bit switch to put DC on this section, which will stop this train. Now, if the train is going over here and released it, if it's green, then when a train comes in here, it doesn't need to stop, and the test contact won't affect it. It'll keep on going because DCC current will remain on this section here. You could also think of this thing as kind of you could call it a trigger, because when your train goes over the red contact and sets the DCC bit switch to red, you know you want to stop the incoming train, but you don't want to stop it till it gets all inside the block. Again, you can't have a train straddling these gaps or you'll get a short from the metal wheels. So you got to make sure the train is all the way inside the block, and then when it gets to the test track contact, it essentially triggers the event that changes this track power from DCC to DC to start slowing this train down. Due to space constraints, I can't get too much of this layout in the camera at once, unfortunately, but I'll just try to handhold it here and walk around the layout. Again, you can see the command station and the crossover, and following the layout, the direction the trains are going to go, they're going to go around the end there and coming down the straight section and come around this corner and then up around here and back to where we started. So over here, this is the end of the brake section. You can see I've got one of these LGB, the old number is 1015T, but basically all this is doing is just making a gap in each rail to isolate this section. So this is the end of the stop section. This Santa Fe diesel is sitting in the stop section. If we follow this backward, we go over here and you can see the same thing. There's another one of these LGB 1015Ts in here again that just makes a gap between both rails. And then going around this curve, you can see right where that yellow ruler is the test track contact, i.e. we can call it the trigger contact. This actually initiates the slowdown of the locomotive, because when you come into a red block, something's got to tell the system when to switch from DCC to DC to start slowing that train down. And it said previously that can't happen until the entire train has gotten across this gap and is all into the brake section. Otherwise you can get a short between the brake section and the regular main line. And then going over here, this track contact in the track where the red piece of wood is, that's the brake track contact, or we could say the brake reed switch. So the idea is being when the train is cleared, when the train is pulled out of that section, it sets it to red behind it, so the next train coming in will be stopped where that red diesel is. And then when that train goes over the crossover and goes around the inside loop, and it'll come through here where that black diesel's sitting, go out onto the outer main line and go over to this track contact. That's the release contact, or we could call it the go contact, because when the train has passed through here and has gotten out of the crossover, it's now safe for the next train where the red one is sitting to start up and come into the crossover area. And just by way of note, I've actually got an LGB track contact here, and I've got an LGB track contact over there, and then I've got one of the, this is either a DCC-Bitswitch or a Railroad Concepts reed switch. It's just a basic reed switch over here. It's probably better to use these. I think this is what DCC-Bitswitch provides. I'm kind of mixing here, which is a bad idea, but as long as I can get this display to work for the video, that's all I needed. We'll start this up with just one train on a track, and hopefully you can see the train going around tripping the different track contacts. Right now the bit switch is set to green, and when it crosses over this reed switch here, you can maybe see it flip to red. See the bit switch went to red. Now when that train comes around and goes over the green release contact, it should switch back to green. Now there it went back to green. Since the bit switch is green, when the train enters the stop section, it'll go over the test contact over here, but since it's green, it won't stop it. There it set it back to red again. There it's going to set it back to green. You see the bit switch went back to green. Now I'm going to manually set it to red. Now that bit switch is red because I manually set it. When that train reaches the test contact, it's going to switch to DC, which it did, and bring that train to a stop. Now that train will wait in the brake section until another train, if there was one on the track, went through here and went over the release contact so that train could start up again. Now since there is no second train, I'm going to manually set that to green. You can see it went to green, and that train is starting up again. You can see with only one train on the track, such as the system is operating now, what we've got essentially is what is sometimes called a time station stop. A single train goes around the track and stops at the station for a certain amount of time and then pulls out. If you had a timer on this to set it back to from DC back to DCC, instead of me manually flipping with the magnet, you'd have a time station stop. And in fact, there is a DCC bit switch unit made called a timed stop that does just that. It's got a timer, and you use a single track contact, what would be the equivalent of the yellow test contact, to stop the train at a station, and it times out and automatically takes off again. Now we'll go through this same exercise of starting the train up and running it around the loop, and using this magnet to manually set the block to red so it'll get stopped in the brake section. The only thing I'll do differently is I'll turn the sound on so you can listen to the sound effects. So that engine is sitting there idling with the sound on, and again it'll start up whenever the other train goes over the release contact. In this case I'll use the magnet to manually switch it on and it'll start up again. Just for review, the beginning of the stop block is over there where that orange note card is sitting. I'm going to zoom in on it here if I can. Right here is the beginning of that stop block. When I say stop block, that's the isolated section that the DCC-Bitswitch will switch from DCC track power to DC track power. Now, going around the stop block, the way the trains travel, they go around here. And there where that yellow is, that's our test track contact. That's the actual place where if the bit switch is set to red when the train goes over that track contact, it actually changes the current from DCC to DC. And then continuing around the stop block, the other end of it is down about where that other yellow note card is. You can see there's a note card to mark the end of the stop block there. Now we've got 2 trains on the track. I'm going to start both of those up and we'll watch those run. Notice the red train stops in the stop section, same as before. Now it's waiting for that black engine to go through the crossing. It just went over the green track contact, so that allows the red engine to start up again. Notice how when they stop, we have the headlight stays on. The headlight on the red engine isn't working, otherwise that headlight would be on also. I've got the camera the lower angle so we can see a little bit more of the track. Again, the red engine stopped until the black one goes over the green track contact, clears the crossing. Now it allows the red engine to start up. I'm going to go put the lights. Got the same operation as before. I just reduced the lights to a lower level so you can see the maybe the signal on the light on the DCC-Bitswitch operating a little better. May be able to see the DCC-Bitswitch light as red. Now in a second it'll trip the green. There it went. The red engine tripped at the green, so it allows the black engine to start up and proceed through the crossover. Now it's still red. It's just stopping the red engine as it comes into the block. The black engine is heading for the green contract. It'll switch it to green, which allows the red engine to start up and proceed into the crossing. Here we are, the same system as before, except I took that red GP7 diesel off and I put on a green LGB diesel. You can see it sitting there. This is one of the very first engines, I believe, that LGB produced with a built-in decoder. It's one of the, came with the original MTS multi-train system set. It's so old we can't adjust anything on it. I can't change the engine number nor the momentum or anything, but it has a little bit of momentum built into it, so it operates reasonably well on this system. So we'll start the system up and you can see that green LGB diesel operating. You can see on the black engine I adjusted that momentum to bring it around pretty close to the end of the stop block, just so that the camera would pick up the headlight being on. Now if you watch the green engine, when it hits the trigger contact, it stops pretty soon, because as I said, I cannot adjust the momentum on that engine, but it does work okay on this system. It just starts and stops a little bit faster than ideal. They tell me with these old engines you can maybe adjust the momentum doing something that they call register programming, but at the moment we don't know how to do that. It's kind of an old way of doing things that people don't know around here. I put the red diesel back on the track, so we had the original two engines, and I put a piece of a cardboard box over top of the DCC-Bitswitch to hopefully put it in the shadows and make the light glow a little brighter. So I'll turn these engines on again and you can just watch them run through the crossover again with the camera a little bit closer. You can see pretty much everything here except the green release track contact, which is down in front of the camera but out of sight. You can see that red engine coming to a stop. The black one is going across the green contact, and you can maybe see now the bit switch to green. Now the red one's traveling over the red brake contact and switched the bit switch to red. That sets up the stop block back in the rear where that black engine came into view. When it hits the trigger there, it switches that track to DC and stops that engine. Now the red one's going to go over the green contact. You can see the bit switch went to green. That switches the brake section back to DCC, which allows that red one to start up. You can see it switched the bit switch to red, so that red engine in the back is entering the stop section. Right about now, the trigger will switch the track contact from DCC to DC. And basically you can vary the CV4 setting, the acceleration setting, to how far these engines drift. And of course, when you adjust the speed of the engines, that affects how far they coast also. So you have basically two variables for each engine you can manipulate. And of course, the position of the trigger track contact can be changed further back to make them stop further back if you wanted to. I've got them coming fairly close to the crossover section just so the camera will pick up the headlights and the strobe lights. So you can see in this little demonstration layout, the Bitswitch is really doing two functions. It's keeping the trains separated so one never catches up to the other, and at the same time it's stopping them in front of the crossing so that they're never in the crossing at the same time. See, the black one stopped. The train that's on the outside always waits where the red one, until the red one goes through and clears that crossing, and then it can proceed. Now we'll do one more run with these same two engines, same as before. The only thing different is I'll start the sound on both engines. This will be a little bit noisy. Keep in mind that this was on an outdoor layout where these are typically used. These engines would probably be further apart from each other than they are in this room. They never get more than 6 feet apart. Here we go. We've been talking this whole video about how this DCC-Bitswitch system uses DC in the brake section to stop a train that's been running on DCC. The DC, it's generally better to have it reverse polarity. The DC can be going either direction, forward or reverse, but it's better to have it going reverse. The red and black engine I've been using as demonstrators, those engines have Zemo decoders in them, and they'll stop on DC in any direction, either direction I should say, forward or reverse. However, some engines like that green LGB diesel sitting over there that we were running earlier, that'll stop on reverse DC, but if you put forward, if you switch the track section suddenly from DCC to forward DC, it keeps right on going. So better to have it set up with reverse DC. And how you can tell that, for large scale in the direction of travel, the left rail is positive. In other words, if you're sitting looking down the track the way the engineer is seeing it, the left rail is positive for normal forward direction. For reverse DC, then the right rail is going to be positive. This is opposite at smaller scales, incidentally. The NHOS 2-rail O gauges, their right rail is positive in forward direction of travel, but the large scale is the one that's different. Normal direction of travel, left rail is positive. Reverse direction of travel, like we want here, the right rail will be positive. And I'll demonstrate that by running the red engine into the block and switching it to from DCC to DC. And then there's a ancient Stein sitting back there from the 80s. It's just a plain old analog engine. I'll put that on the track, and when it sees that reverse DC, it'll take off, even though my big DCC engine is stationary. Now there's our engine heading for the test track contact, at which point DCC will be changed to DC, and you can see that engine stop because it's sitting there on reverse polarity DC. Now I'm going to take this old, just as a demonstration, I'm going to take this old analog engine, put on the track, and you can see it takes off because it runs on DC current. So that's an easy way to tell whether you've got reverse polarity DC or forward polarity DC. Is just put an old engine with no decoder on the track, and if it takes off backward like that one, that engine does, you've got the polarity the way it's probably best to have it. Let's take a look at these magnets. If you're familiar with LGB, you've probably seen these magnets. They fit on, they snap on the bottom of most of the LGB engines. For example, this black diesel we've been using, it has kind of a ridge underneath it, and you can see maybe I was able to just snap the magnet on the bottom of this locomotive, and it seems to work fine. Now that big red diesel, that's a USA Trains engine, and since it's not built by LGB, they didn't give us that ridge, but there was a flat spot under the engine. I was just able to rubber cement one of the same LGB magnets on the bottom of this engine. Now this old diesel here, that one has the ridge, and I was able to snap one of these magnets on the bottom of this engine, but for some strange reason these are made, they stick down too low and they hit on the track contact. So I tried taking a separate magnet without the metal casing in it, just a magnet by itself, and rubber cementing it on there, which I was able to do, but that didn't trip the reed switches for some strange reason, which I can't really explain. So I ended up taking one of the round magnets, I guess they call these rare earth magnets, and rubber cementing that on the bottom, and it seems to work okay. These are probably the best thing to use anyways, because these magnets here are a lot stronger than these LGB magnets, not to mention being a lot less expensive in addition to being stronger. So this is probably the better way to go. Incidentally, this little blue LGB Steins engine comes with a built-in factory decoder. In other words, it comes right out of the box new with a decoder. I was planning on using this one, but it won't work. For one thing, it doesn't stop on reverse DC. It's kind of backward. It will stop on forward DC, but the second thing, it takes so long to stop that it would need a really, really long block to stop it in. This was demonstrated in the previous video 807, so I guess the moral of the story is even though your engines come out of the box with a decoder, you can't count on them being able to be used for a system like this. Now if we use the DCC-Bitswitch set speed 0 generator, that would probably stop this engine okay, but for the simple DC brake generator like we're using in this video, I was unable to use this engine. One more comment on positioning these magnets. If you look at the way it's done in this video, this is not really the right way to do it. I refer you to pages 11 and 12 of the DCC-Bitswitch manual, but Fred basically says if the magnet's in the center of the engine, thus it's coming down the center of the track, it'd be better to have the magnet so just the tip is sticking out. In other words, he says you want the center of the magnet, the center of the magnet going over the tip of the reed switch, not the center of the reed switch as I have it here. And even better, if your layout arrange it allows it, it's better to have the reed switch parallel to the rails like this one I just laid in here, so the reed switch is going parallel to the rail. So I just did it quick and dirty so I could do this video, but keep in mind what I'm showing here is not really the good way to do it. So far in this video we've been talking about running in automatic mode. Remember also that the Bitswitch has a manual mode. What is manual mode? Manual mode is basically where you essentially bypass the Bitswitch system so it has no effect on the track, and you can run your trains entirely in a manual mode as if the Bitswitch system, however many of them you have, as if they were never even there. Let's take a look at this analogy. What I've got set up here is actually in my laundry tub, but if you use your imagination a little bit and consider this to be a command station hookup, here we have a DCC command station. Here's our DC brake signal generator, and over here we have the AB wire coming out, which is DCC. That's actually hot water here, but DCC. Over here we have the CD wire coming out, which is DC when the thing is in the automatic mode, and this is cold water in this case. Now further down we've got our bit switch, which is really the faucet for the laundry tub, but this is our bit switch picking up one of these two lines, either cold or hot water, or using our analogy DC or DCC current. The bit switch takes whichever one is required to the track to do what it's supposed to do and sends that out to the track brake section, which is this hose. So for this hose you can have either cold water going out it or hot water going out of it, depending on which pipe the faucet's picking up off of. So again, using our analogy, there's a switch on this DC brake signal generator, recall, and you can throw that switch from automatic to manual. If you throw it to manual, it puts DCC on this line instead of DC. So now operating in the manual mode, now we have DCC on this wire coming out also, or in the case of our laundry tub, let's say we switched it so hot water was coming down this pipe as well as this pipe. So regardless of which way you turn the bit switch down here, you'd have hot water coming out the hose to the track section. In this case it would be DCC current coming out to the track section regardless of which way the DCC bit switch relays were thrown. It would have DCC coming into it on both sets of wires, so it will always put DCC out. This would be manual operating mode, and the position of any of these bit switches on the layout, however many of them there were, one like our test layout, or if you had a layout with 10 or 20, it wouldn't matter which position they were in because they'd always be getting DCC on both their inputs wires and sending it out to the brake sections. Here we are back at the layout, just reviewing the components. We have our command station here, going out to our DC brake signal generator here, going over to our DCC bit switch, block bit switch unit here, and then the power going out these wires to the track, to the brake section of the track. Now when this is in the automatic mode, like we've been running it so far in this video, there's always DCC going out the AB wires over here. That never changes. But on these CD wires, the wire pair on this side. In automatic, like we've been running it so far in this video, you have DCC going down these two wires, and then the bit switch, which is simply 3 relays. It's not really that complicated. It's clever, but not complicated. This thing sends out to the track the appropriate signal. It either sends out DC if we want to stop the train, or if the thing is green and we don't need to stop the train in the brake section, then it sends out DCC. So it switches back and forth between using these two inputs. Now if we throw the thing from automatic to manual, which is done by flipping this lever here, that changes, that basically bypasses the rectifier, so there's always DCC now coming out this wire as well as this wire. So you've got DCC on this wire as always, and now with this thing thrown to manual, you have DCC on these two wires instead of D. That means regardless of which way this relay throws, and the black one is actually the power relay, I believe, regardless of which way this thing throws, you're always sending DCC out the track wires here. So in manual mode, any bit switches on the layout, like this layout has 1 bit switch, but any bit switches, whether it be 1 like here or 10 or more of them on a layout, regardless of which position they're in, they're always putting DCC on the track everywhere. So essentially they're invisible. It's like they're not even there. So as DCC-Bitswitch claims, you can run your system in manual mode just like you normally run it. Then when you want to go back to automatic, you just simply throw this switch from manual back to automatic, and it goes back to automatic operation. Right now the brake signal generator is still in the automatic position as it's been for all this video. I'm going to start this engine up. When it goes across the green release center here, I'm going to use this magnet to manually set it back to red by touching this magnet to the red brake sensor, and that'll stop the engine when it comes into the brake section over there, just as it's been doing since the beginning of the video. But then what I'm going to do is I'm going to go over to the DC brake generator and switch it from automatic to manual, which will put DCC into that brake section, and you should see that engine at that point start up and pull out of the brake section, even though the bit switch is still a red, because when I flip the switch from automatic to manual, when it puts DCC on the track, then the position of the bit switch becomes irrelevant. Then I'll let it run around one more loop, and I'll set this manually to red again with the magnet, and it should cruise right through the brake section without stopping, because with it set to manual, it's getting DCC everywhere. Okay, the engine set it back to green. So I'm going to go over here and manually set it back to red. Now it's red. That engine should stop as it normally does when it comes into the brake section. There it went over the test sensor. You can see it's cruising to a stop. And again, it's going to wait there until a second train goes over the green release contact to release it. Otherwise, it's never going to go anywhere. But what I'm going to do now, I'm going to switch this brake generator from automatic to manual, which is now putting DCC into the brake section regardless of the position of the bit switch. Now the engine just set that bit switch to green. I'm going to go manually set it to red. But because the brake signal generator is in the manual mode, it's putting DCC into that section even when the bit switch is red. And you see the engine just goes and ignores it and goes right through. So again, just repeating what we said earlier, when the brake signal generator is in the manual position, then the bit switches essentially become invisible. If you have an NCE DCC system such as I do, one other option you have different than DCC-Bitswitch is hooking up one of these devices called a mini panel. But this has to be used with an NCE system. If you have a brand other than NCE, you can't do this. But if you have NCE, one nice feature of this is you don't have to cut any blocks in the track or anything. Your track can be pretty much continuous. It works well with one loco. However, if you get two locos or more locomotives on the track, it gets cumbersome with this because every time you send the command, you basically have to tell what engine number you're addressing. If you have different engines, you're trying to handle a lot of different numbers, and it gets pretty complex.